In this video, we will be talking about combinations. Our learning objectives here are to distinguish between a combination and a permutation, how to find the number of combinations of n objects taken R at a time, and then how to use the combination rule in conjunction with the fundamental counting principle. In the previous video, we talked about permutations, and we looked at examples of how when you're selecting a certain number of objects from a larger group of objects, how many ways can you select that number of objects and order them in a specific way? When order matters in a selection, we call it a permutation. But when order is not important, we call it a combination. A selection of objects without regard to order is called a combination. Let's explore this idea with an example. Example 1, comparing permutations and combinations. Given 4 housemates, Ruth, Elaine, Emma, and Jasmine, list the permutations and combinations when you are selecting 2 of them. We'll start with permutations. So with permutations, the order matters. Right? So we're talking about how many ways can you select one person followed by another person and order them in a specific way. So here's my permutations. Let's see. I could select Ruth first, followed by Elaine. I could select Elaine first, followed by Ruth. I could select Ruth first, followed by Emma. I could select Emma first, followed by Ruth. I could select Ruth first, followed by Jasmine. I could select Jasmine first, followed by Ruth. And let's see, what else? We could do Elaine first, followed by Emma. We could do Emma first, followed by Elaine. We could do Elaine, followed by Jasmine. We could do Jasmine, followed by Elaine. Emma, followed by Jasmine. And then one more, we could do Jasmine, followed by Emma. Okay, so this is the total number of ways that I could select 2 names from a group of 4 names and order those names in a specific way. Now, for combinations, the order does not matter. So for example, if I have Ruth followed by Elaine and Elaine followed by Ruth, those are separate permutations, but they're considered the same combination because they're the same 2 people. With the combinations, we don't care about order, right? So if I don't care about order, right, then basically we could have something like this. Ruth, followed by Elaine. Now, I'm not going to put Elaine followed by Ruth because we don't care about the order. All we care about are the 2 names, right? Ruth, followed by Emma. Ruth, followed by Jasmine. We could have Elaine, followed by Emma, Elaine, followed by Jasmine, and Emma, followed by by Jasmine. Okay. So for permutations, we care about ordering the names in a specific way. Combinations, all we care about is how many ways could you pick two names from a group of four names. And we don't care about the order, right? So there are 6 combinations and 12 permutations. Now, it's really helpful in our study of counting and probability to be able to decide if a given selection is a permutation or a combination. So here's a couple of examples. Decide if each selection is a permutation or a combination. Part A, from a class of 25 students, a group of 5 is chosen to give a presentation. Notice that this does not say anything about order. There are no distinct roles for the 5 group members, so order is not important. So this would be combination. Let's write this here, combination. Okay. The second one, a starting pitcher and a catcher are picked from a 12-person intramural softball team. But this is a permutation, and that's because each selected person has a distinct position or distinct role, right? So the order actually does matter in that situation. That would be a permutation. Okay? Okay, so in the previous video, I showed you a formula that involves the factorial notation that we use for calculating the total number of permutations in a given situation. In this video, we want to come up with a formula for determining the number of combinations. It will be a similar looking formula. It will also involve factorials, but it will look a little different. So this example here will help us derive that formula. Part A. A college instructor gives students a list of 7 projects to choose from, and each group has to do 3. A week into the course, each group has to submit a list of the projects they're choosing and the order in which they plan to present those projects. Use a permutation formula to find the number of ways a group can choose. Well, the permutation formula that we would use is the exact same one that we used in section 10.2 in the previous video. So that formula looks like this. N factorial over n minus r factorial, where n is the number of items in the group and r is the number of items that you choose. Okay. So in this particular case, it says, you're supposed to select 7. So you've got 7 projects. Each group has to do 3, and it does say that they're being asked to submit the order in which they plan to present those projects. So the order matters. The order is important here. So that's why these are permutations. My value of n here is 7. My value of r is 3. So this is equal to 7 factorial divided by 7 minus 3 factorial. That's equal to 7 factorial over 4 factorial. This is equal to 7 times 6 times 5 times 4 factorial over 4 factorial. Cancel. So this just simplifies down to 7 times 6 times 5, which is equal to 210. Okay, let's move on to part B here. Midway through the first week, the instructor decides that groups don't need to provide an order. What would you divide your answer from part A by to account for this, and why? Okay, so if we were to list all the permutations, every time we listed 3 specific projects in different orders, we would be listing the same 3 projects 6 times. Why 6? Well, because that's the number of ways that we can order 3 projects. The number of ways we can order 3 projects is 3 factorial. 3 times 2 times 1. That's essentially the fundamental counting principle that we talked about last time, which is equal to 6. So to find the number of projects to choose without regard for order, we would take the 210 permutations from part A and divide by 6. Okay, so 210 divided by 6 gives me 35 combinations, right? So this is saying there are 210 ways that you can select 3 projects from a group of 7 projects and order those in a specific way. However, if we don't care about order, there are 35 ways of just selecting 3 projects from a group of 7, right? If we don't care about ordering those. For C, use your line of reasoning from part B to write a formula for finding the number of combinations of n objects taken R at a time. So we can generalize the result from part B. To calculate the number of combinations of n objects taken R at a time, what we did is we took the number of permutations and then we divide by the total number of ways of ordering R objects, which is just R factorial. So this is how we make order not count, by dividing out the number of possible orders. So our combination formula looks like this. It's just the permutation formula divided by the total number of possible orders, which is like that, okay? Okay, so let's present kind of the final formula for this. To represent the number of combinations of n objects taken R at a time, we will use the notation similar to permutation notations, but instead of a P, we use a C. We still use the N and the R subscripts, but we use a capital C instead of P to represent combinations. So here's the formula. The number of combinations of n objects taken R at a time without replacement is denoted by this NCR, and it's given by this formula. The number of permutations divided by R factorial, or I could just write this as n factorial divided by n minus R factorial times R factorial. Let's do an example, another example. While studying abroad 1 semester, Tran is required to visit 10 different cities. He plans to visit 3 of the 10 over a long weekend. How many different ways can he choose the 3 to visit? Assume that distance is not a factor. The problem does not say anything about the order in which they will be visited. All we care about is choosing 3 of 10 cities to visit, right? The order doesn't matter. So this would be a combinations problem where n is the total number of cities, which is 10. R is the number of chosen cities, which is 3. So we're looking at, sorry, let me write that better. If I plug the numbers into the combinations formula, I get 10 factorial over n minus r is 10 minus 3, that's 7 factorial, and then 3 factorial. Okay. I could simplify this down. I could write this as 10 times 9 times 8 times 7 factorial. In the denominator, I have 7 factorial, and 3 factorial is 3 times 2 times 1. 7 factorials cancel. So it's 10 times 9 times 8, and that's divided by 3 times 2 times 1, basically. So that would be a simple calculation on your calculator, but it works out to be 120. Okay. So there are 120 ways that you could choose 3 cities from a group of 10 cities to visit, or just in general, there are 120 ways you could choose 3 objects from a group of 10 objects, if you don't care about the order. Okay, a little side note. I mentioned this in the last video as well, but many scientific calculators have a built-in function that allows you to calculate permutations and combinations easier than just kind of working it out by hand like I did here. In the Brightspace module, there is a video posted for how to use a TI-30 calculator to both calculate permutations and combinations and just factorials in general. The TI-30 is one of the more common calculators, so it's quite possible that's the one you have. Even if you don't, most scientific calculators have this ability. You might need to look at your instruction manual or something. But please watch that other video that's posted in the Brightspace module. And please note that on homework and exams, you are welcome to use that functionality of your calculator without necessarily needing to apply these formulas directly and work out the calculations by hand. Okay, moving on. In some cases, the combination rule is used in conjunction with the fundamental counting principle. Examples 5 and 6 illustrate some specific situations. Example 5. At one school, the student government consists of 7 women and 5 men. How many different committees can be chosen with 3 women and 2 men? So we could think of this problem as having 2 distinct stages. First, choosing the 3 women, and then choosing the 2 men. So it's basically a fundamental counting principle problem. At each stage, though, we have a combination. We can choose 3 women from the 7 candidates using the combination formula where n is equal to 7 and r is equal to 3, right? Because we're choosing 3 women from the group of 7 women. I'm not going to take the time to work these out in detail because we've gone over several examples of how to do that. But again, you are welcome to use your calculator to do this. But this works out to 35, okay? So there are 35 ways that we can choose 3 women from the group of 7 women, okay? Okay, let's put this. For men, right, there are 5 men. We want the committee to have 2 men, so we need to figure out how many ways can we choose 2 men from a group of 5 men, right? So this would be 5C2. This works out to be 10 ways. Then we use the fundamental counting principle to multiply, right? So there's basically 35 ways that we could choose the 3 women, multiplied by 10 ways that we could choose the 2 men. Altogether, there are 350 different potential committees. Okay? So there are 350 ways that we could choose a committee that consists of 3 women and 2 men when we are choosing from a group of 7 women and 5 men. Okay? That's what that's saying. Example 6, designing a calendar. To raise money for a charity event, a sorority plans to sell a calendar featuring pictures and bios of some of the school's most popular athletes. They will need to choose 6 athletes from a pool of finalists that includes 9 women and 6 men. How many possible choices are there if they want to feature at least 4 women? Okay, since we need to include at least 4 women, there are 3 possible compositions, right? We could have 4 women, 2 men, We could have 5 women and 1 man. We could have 6 women and 0 men. These are all the possible ways that we could have a committee that has at least 4 women when the committee will be a total of 6 people, right? So we're choosing 6. Okay, so and the pool of finalists includes 9 women and 6 men. Okay, so for this first scenario here, 4 women and 2 men. Again, we have 9 women finalists, right, and 6 men finalists. So this right here, just put it up here, would be a number of ways of choosing, 4 women from a group of 9, and we multiply that by the number of ways of choosing 2 men from a group of 6, okay? If you work out those combinations separately using either your calculator or the formula, you would get 126 for the first one and 15 for the second one, which works out to be 1,890, okay? For this scenario, for the 5 women, there are 9 women finalists. So the combinations would be, how many ways could we choose 5 women from a group of 9 women, right? So that would look like this. And we're multiplying that by another combination. This would be, how many ways could we choose 1 man from a group of 6 men, okay? Okay. The first one is 126. The second one is 6. These work out to be 756. Okay. And then lastly, we have, how many ways can you choose 6 women from a group of 9 women? So that's 9C6, multiplied by the number of ways of choosing 0 men from a group of 6 men. Okay. How many ways can you choose 0 men from a group of 6 men, basically, right? This works out to be 84 times 1. Essentially, there's only one way that you can choose 0 men, right? So, and this works out to be 84, okay? So you want at least 4 women, right? So this top number here, that would be the scenario that involves exactly 4 women. The next one, exactly 5 women. And then lastly, exactly 6 women, right? So the total number of possibilities, say total number of possibilities is going to be the sum of those 3 numbers. So 1,890 plus 756 plus 84, which equals 2,730. All right. This is a good time to talk about the significance of the words and or when applying counting techniques. In example 5, we needed a committee with 3 women and 2 men. This led us to conclude that we could think of it as a 2-stage process and multiply, which is really an application of the fundamental counting principle. In example 6, we ended up choosing between 3 possible options: 4 women, or 5 women, or 6 women. In this case, we found the number of possibilities for each and added them. So typically when we're talking about these sorts of problems, the word and often corresponds to multiplication, and the word or corresponds to addition. Okay, the table on this next page summarizes all of the counting rules from sections 10.2 and 10.3. It is good to know the formulas, but definitely more important to understand the situations that each formula is needed for. Here's that summary table. We haven't really covered this one right here, permutation rule for duplicate objects. So really focus on the fundamental counting principle, the permutation rule, and the combination rule. And again, I would really encourage you to watch that other video on the Brightspace module, which will tell you how to use a calculator and the built-in functionality to do factorials and permutations and combinations. For now, we'll wrap this video up. Thank you for watching.